somewhere deep in the Australian bushland.
It's been days since I've eaten. Might be time for me to go and forage some food. Damn, my phone's run out of battery again. If only I had access to some infinite energy source out here in the remote wilderness.
As hard as he tried, our adventurer could not solve this problem on his own. He needed the help of his two big-brain engineering colleagues, Atkins and Christopher.
Guys, you never guess. My phone ran out of battery on my latest trip.
Oh no. What are you going to do about it?
I reckon you should build a solar-powered phone charger with an integrated boost converter.
Not the internet again.
And here starts our story of SOLA2051. This year, we had to work on the project completely remotely. What did this mean? A lot of hours working alone without the direct support of tutors and classmates, as well as missing out on a few fun parts of the course.
Yo, we gotta make solar panels. Oh.
Fortunately, we had a great lecturer who was very nice and interactively taught us all the ins and outs of boost converters, solar panels, and other components required, as you can see here. We learned about many interesting things just to build this solar-powered phone charger, including the Arduino, a device that can measure and supply voltages. We also learned about solar cells and their IVs, and how all this stuff works, and much, much more. One of the most important components was, of course, the solar panel. We needed to characterize the panel so that we could generate a fitted IV, and therefore allowing us to simulate the panel in LTspice. Through some complicated maths and equations and magic, we got these values. Our initial calculated values were not perfect, however, and it took some tweaking to get the fitted IV curve to match the given data. Next, we chucked it in LTspice, and boom, solar panel modeled.
And now, time for simulations.
All components of our circuits were simulated in LTspice. This included the solar panel, which is the power input, the boost converter, which is used to boost the voltage of the solar panel input high enough so that a phone could be charged, and the PWM, which is connected to this MOSFET switch on the boost converter and effectively controls how voltage boost is outputted. But why would you spend time simulating when you can just have fun building the damn thing? It turns out, LTspice holds all the secrets to how a boost converter works, and it allowed us to understand what each component did and therefore allow us to choose the best components to maximize the boost converter's efficiency and our ability to control it.
For example, this 1 nanofarad capacitor, according to LTspice, increases the frequency of the PWM so it's operating at its highest frequency, reducing power loss from the inductor, and hence maximizing efficiency.
Now that's a lot of
Power.
From some of our previous subjects, we knew that tilt and azimuth angle had a big impact on the output of a solar cell. As such, we used a state-of-the-art mounting structure to allow us to change the tilt of the panel on the fly. Temperature also plays a big role, with power being derated by approximately 0.4% per degree above 25 degrees Celsius. Using some scrap aluminium foil, we created a makeshift heatsink to increase the effective area and hence increase the convective heat transfer away from the panel. Now the software we used to control the Arduino, and effectively the boost converter, was LabView. Our LabView VI essentially allowed us to make important measurements from our Arduino, including the input and output power, as well as insulation. Furthermore, we could alter the duty cycle and therefore the boost output, both manually and automatically, to attain the desired output power. It was also capable of uploading this data to the cloud. However, one of the largest problems we had to tackle was the ability to measure solar insolation every 3 minutes. Every 3 minutes, the duty cycle is set to 1, essentially short-circuiting the panel, allowing us to get a value for the insolation.
With all the pieces finally together, we just required a clear sky with plenty of direct sunlight to maximize our input power. Fortunately, we had exactly that on the test day, which essentially helped us achieve great results. On the test day, we achieved great power, with Dylan almost reaching 700 milliwatts. This was roughly 85% of the theoretical max power expected from LTspice simulations. However, having a lower than expected power could be explained by many resistances and wires in the breadboard which were used to build the circuit. These limiting factors weren't modeled in LTspice. Overall, we are pleased with the overall result, and if anything, it was our amazing designs such as the heatsink and mounting which allowed us to even achieve high power levels.
Thanks to the Group 3 solar boost converter, I never have to worry about running out of charge ever again.